So multiple regression analysis, also called a multivariate regression analysis, is a situation where a variable, say y, may be depending on many variables. Those other variables, we call them independent variables. A good example, maybe our cost of production in the business is heavily relying upon, let's say, the raw materials that we are buying. Therefore, the number of units that we are going to produce are likely to bring a change in relation to our cost. But maybe we also have something to do with the storage. So the storage facility, depending maybe on the region, could also be influencing our costs to be incurred in the business. Therefore, we end up having more than one independent variable to talk about, as the cost depends now on many factors. And if you remember in the bivariate analysis, when we were looking at the coefficient of determination, we said 74% of what happens to our dependent variable is being determined by that one independent variable, meaning the other balance of, let's say, 26% is now going to be determined by other variables which were not actually involved in the study. So that other balance means that there are other variables that somebody could have taken into consideration into the analysis of whatever the area could be. Let's say we are probing on the sales. Let's say we are probing on something like the cost of production. Maybe we want to see the performance in the business. So as we analyze this, it could be depending upon so many variables in the analysis. And therefore, when we hit more than one independent variable, we now talk about the multiple or the multivariate regression analysis. And in this case, we have what we call the dependent variable. We can call it y. And for each of our independent variable, it will have a corresponding coefficient. So in writing the model, the regression model, we will have a constant on its own. We can call it B naught or just an A. Then talking about an independent variable, let's say x1, it may go with a corresponding coefficient of B1. So if we read our equation like that, this is called a bivariate regression analysis. But we are saying in the multiple regression analysis, we have got a number of the variables, not just one. They are quite a number, and therefore we need to include all the other independent variables. Say we have another independent variable like x2, which could be having a corresponding coefficient of B2. And we do the same to all the other independent variables. Of course, it will depend on how many there are in a given analysis. So I may put some dashes. Of course, one needs to go up to the point where we have the last independent variable. Let's assume we have up to the mth independent variable with its corresponding coefficient known as Bm. And that is how we write a model in case we have what we call more than one independent variable in the question. So if we are asked to find or to write down the model under the regression analysis, that is with the multiple independent variables, make sure that you can be able to consider the corresponding coefficients to each and every of the independent variables. And as you do so, you are able now to write down the regression analysis, noting that we have a coefficient on its own. The constant A or the constant B naught does not correspond to any of the independent variables. Okay. Now I have a question that I would wish us to maybe go by, which will act as our example. In December 2009, Hope all of us, we can be able to see the past paper. Question number 4, part number A. I read through the question. A consultancy firm carried out a survey to determine the level of job satisfaction among the employees of a given company. A multiple regression analysis was done, and the results were as follows. Again, if you remember, we said in the multiple regression analysis, you find that working with these independent variables manually, because there are many, our work will become tedious. So a computer may be used, which generates us with our output or a solution. And by so doing, we are able to find the solution, which we can now be able to interpret. I repeat, as a result of the independent variables being so many, we are now able to have the regression model written down, that is from a generated computer solution. The computer, using some softwares, is learned, and we come up with a solution, which our case now will involve the interpretation of that solution. So we have got the individual analysis of the variables. We have the independent variables x1 all the way to x7. And for each of the independent variables, there's a computed standard error, like the one we were saying, constituting our x in the bivariate analysis. How are we able to come up with the standard error? Now, that is already provided. The estimate, that is the coefficient of estimate, is already given. That is column number 2 there in your analysis. And we also have the constant, the B naught, given there with its estimate 13.7172. So with this, we are asked on the next page, we write down Roman number 1. Roman number 1, we write down the regression model for the above data, where we are given x1 as the age, x2 is a monthly salary, x3 the experience, x4 the education level, x5 the gender, x6 we have the responsibility, and x7 we are given the number of years in service. Now, with all those variables given, we are told, can you write down the model? The regression equation is going to look at, let's find out. I will take y to mean the job satisfaction. So let y, you can write there, let y represents the level of job satisfaction. That is our survey, that is our dependent variable. Let y represent the level of job satisfaction among the employees. So our y as our dependent variable is going to be given by, I'm going to start with the B naught. B naught is my constant, whose value is given as 13.7172. Then we have our B1, the corresponding coefficient to X1 is a negative. This is minus 0.0312 with the corresponding independent variable x1. We move to x2, whose coefficient corresponding there is a positive 0.9. 86, sorry, going with x2. The next coefficient is that of x3, which is also a positive 0.1284, and this is going with x3. You see, I'm following the general form that we had earlier on. For every, this should be x3, sorry. For every coefficient, it has its corresponding independent variable. For x4, we have a positive again, 0.0592, of course going with x4. Then x5 has a coefficient of again positive 0.1284. This is going with x5. Then for x6, we have a negative 0.6326, going with x6. And then we have a positive 1.2806, 0.5 there, going with x7. And that is what we call our regression model or our regression equation, which we have picked the constant b0, and for every of our independent variable here, x1 all the way to x7, we have got a corresponding coefficient of estimate. So as you write the model, remember the general form of a multiple regression analysis. We are also asked to find the meaning of the estimates of x1 and x2. These coefficients minus 0.0312 plus 0.1986, what is their meaning in our analysis? If I take you back to our area analysis, we had an equation, the y estimate, even this one you can call it the y estimate, is a plus bx. We said the constant b here has a very big meaning to us because it does display how the x and the y are related. The form of relationship existing between the y and x is displayed by the constant b. So the same constant we have, only baptized as b1, b2, b3, we need to look at it, and if it is negative, there exists a negative relationship between the y, that is our dependent variable, and the mentioned independent variable. If it is positive, again, we'll say there's a positive relationship between the said dependent variable and of course the independent variable in question. So we can begin with x1. x1 has a coefficient of negative 0.0312. What does that one mean? This shows that the minus 0.0312 represents a negative relationship between the level of job satisfaction and the age. The age was our variable x1. X1, which is the age, and the job satisfaction, the y, are negatively related as a result of our coefficient here being negative. How about the coefficient of x2? X2 has a coefficient of 0.9186 and it is positive. So our comment is that there exists a positive relationship between the X2, which is the monthly salary, and the job satisfaction. Or rather, the monthly salary affects the job satisfaction positively. There's a positive relationship between those two variables. And we can also take our time and define any other coefficient that we have here, its meaning as we relate that independent variable to our dependent variable. If the variable is positive, a positive relationship. If it is negative, a negative relationship. For example, going by the coefficient of x6 here, we would say there exists a negative relationship between the level of job satisfaction and the level of responsibility by the manager, or maybe somebody not being a manager. I repeat, since our coefficient here is negative, then our job satisfaction, the y, and the level of responsibility, that is our x6, they are negatively related. And you can pick, for example, that of x7. Since it is a positive, then you will say there exists a positive relationship between our x7, which was the number of years in service, and of course the level of job satisfaction, which is our dependent variable y. So that is the interpretation that one should be able to give for each of the coefficients that we have here as we relate it to any of the variable given. And of course, you're taking that variable with the corresponding coefficient. Now, how does that independent variable influence the dependent variable in your study? We are told to test on the significance of each of the variables, as to the job satisfaction level using the 5 level of significance. Before we do this, I would wish to start by analyzing what we call the Anova Table. The Anova Table is the one we call the analysis of variance. The table given there so that you're able to pick a number of items from that particular table. So the analysis of variance, I'll shorten that. We usually call it the Anova Table. Because it's from this table we'll be able to get a number of the details that you require in our testing. The Anova Table. So this Anova Table, usually we start with the source. And then we have the effects of the regression. Some books, they call this one the model. And then we have the error term. You may also find some books scoring this residue, the remainder that has not been taken care of. You can call it a residue or an error term, because not always we are accurate in our estimations. Sometimes you may find there's a difference. So you have the source. Under the regression and the error term, we may be interested in getting what we call their totals. And then we have the degrees of freedom. Allow me to just call this one the DF. So we have the degrees of freedom due to regression, and we also have the degrees of freedom due to the error term. There down, we have the total degrees of freedom. Our next column in the Anova table is usually the sums of squares. If we were in a statistic class, we'll be developing this, but it is not necessary. For us, we will be provided with a computer solution. The sum of squares. Once we have the sum of squares for each of the regression and the error term, again, we'll be able to determine the sum in total. So allow me to call the sum of squares for the total as the TSS, the total sum of squares. And then we have the sum of squares due to the error term or due to the residue. So I'll call this one the SSE due to the error term. And then for the residue, for the regression model, sorry, I'm going to call it SSR, the sum of squares due to the regression model. So when we sum over these two, we'll be able to come up with the total sum of squares. After which we find what we call the mean sum of squares. I'll call this one. You can write it in full. Mean sum of squares. And I'll abbreviate this one as MSS, mean sum of squares. So usually, this one we get only in reference to so for the mean sum of squares, we get only for the regression and also for the error term. We don't find the total. So I'll call this the mean SS, that is for the regression, and I'll call this one the mean sum of squares due to the error term. So how do I arrive at the mean sum of squares for the regression? You take the sum of squares due to the regression and you divide by the corresponding degrees of freedom. By the corresponding degrees of freedom. Also, you take the sum of squares for the error term. You divide this one by the corresponding degrees of freedom, by the corresponding degrees of freedom to determine the mean sum of squares in the case of what we call the residue or the error term. Now, after we are able to get the mean sum of squares, we can now do a test using what we call the F table, and we construct what we call here the F value. The F value computed, or the F statistic, and this is given by the value of the F is given by the mean sum of squares due to the regression. You divide this one by the mean sum of squares due to the error term. And you can now perform a test using the F table if that is actually provided. You may be asked to find or to test the relevance of the study, the whole study. If you are asked to find the relevance of it, you need to determine the F. But if you're testing for each of the independent variables, of course, you may be now using either the student t distribution or the normal table, of course, depending on the degrees of freedom. Now, the degrees of freedom due to the regression may be provided. The degrees of freedom due to the error term may also be provided, but the total degrees of freedom are supposed to be given by n minus 1. The total degrees of freedom, let me write it here. Total degrees of freedom, I can just baptize this one as the TDF. Total degrees of freedom are supposed to be given by n minus 1. So if, for example, you know the degrees of freedom due to the regression, you know the degrees of freedom due to the residue, which gives us the total, and you don't know the sample size, the n, it is possible to determine it using the total degrees of freedom, which are supposed to be given by the formula n minus 1. Of course, for the regression and the error term, it depends on the number of the independent variables that are there. There are also some formulae normally used in the computations, but because we are not doing our work manually, those degrees of freedom given by the computer solution, we just use them the way they are. Now, let me go back to the question where we were having Anova table given by the computer as a solution, and we have the regression model having the degrees of freedom given by 7. The degrees of freedom given by residue is 42, meaning our total degrees of freedom will be equivalent to 49. 7 plus 42, that gives us 49. And this 49 we are saying is the same as n minus 1. So if we want to know, like in this question, we were not given the sample size. Is it possible to tell what is the sample size? Look at this. If the total degrees of freedom n minus 1 is coming to 49, you can see our sample size involved in the study must have been 50. And if you want to use either a table to help you do the test now, could be the normal distribution or the student t distribution, you need to first of all find out what is the size. The n, is it greater than or equals to 30, or is it less than? So which distribution do you go by as you perform your test? The sum of squares we are given for the regression, we have 151.25. And for the error term, we have 143.24. Giving us a total. You can confirm this figure given there, whether it is okay. That is 294.49. You can confirm the total. So that is our table, which goes up to that point where we have provided with the degrees of freedom as well as the sum of squares for the regression, the error term, as well as the total. But now we don't have the mean sum of squares for the regression as well as the error term. We can be able to compute this by getting the degrees of freedom, that is 151, or rather the sum of squares for the regression model, which is 151.25. We divide this one by the degrees of freedom, which is equals to 7, giving us a value of, let's find out. That gives us 21.6 to 1 decimal place value. And our mean sum of squares due to the residue will be given by 143.24. We divide this one by 42, giving us a value of, let's find out. This gives us 3.4. As the mean sum of squares that is due to the residue. Now our F value can now be computed as the mean sum of squares due to the regression model, which is 21.6. We divide by the mean sum of squares due to the error term, which is 3.4. And if we were to conduct a test, supposing that you are given an F value, the table value, as we don't have the table for the F, the Fisher table, but we can be provided with a figure, then we are told to do the test. So you have 21.6, which are dividing by 3.4. That gives us 6.4. So assuming, let me say, assuming maybe at 5% degrees of freedom, or the significance level now provided of your test, maybe 5%. Assuming at 5% level of significance, you're told to test whether this model, the whole of our analysis, is significant or not. And let's say the F table given, assuming the F table provided is, for example, something like 5.8. If our F value taken in absolute terms, if the F value that we have computed here taken in absolute terms is actually a figure that is less than the F table given, assuming this was provided from the table, the F table, the F computed, or the one that I'm calling the F statistic here, this is a computed value. This other one, the one I've written there as 5.8, let's say it has been extracted from the table. So you compare your F computed and the F table, and if your F computed tends to be less than, taken in absolute terms, is less than the F table, then you'll say the model is not significant. I repeat, if the F computant, of course assuming the negativity, is less than the F table, then you'll say the model is not significant. You're testing the whole model. In case you find the opposite now happening, let's say the F computant happens to be greater than, if the F computant is more than the F table, if the F computant, like the 6.4 here, is already greater than 5.8, we would say that the model is significant. That study is significant, and of course, it may be contributing to the field of research work. I repeat, if the F computant is greater than the F table, then we say the model is significant, or the study was significant. Okay. Now, we may wish to do some calculations based on this particular Anova table. For example, I want to talk about how can I get the coefficient of determination using my table. If, let's say, you're given a regression model, which is constituting the workings done by a computer. So you have a solution, the Anova table is provided, and then you want to find the coefficient of determination. How do we go about that? A point to note. From the Anova table, you can write that from the Anova table, the coefficient of determination, which we were calling the R squared, coefficient of determination, or what we call the R squared. We said when you're writing in words, use capital letter R, and if you're writing it in abbreviation, then we use small letter R squared there. Is given by the coefficient of determination, or R squared, is given by the sum of squares due to the regression divided by the total sum of squares. I repeat, the coefficient of determination is given by the sum of squares due to the regression divided by the total sum of squares. For example, in our case here, we would take 151, we divide by 25, we divide by 2.5 there, and then here we are dividing by 0.24. 151.25, we divide by 143.24 there. And that would give us what? No, this should be total sum of squares. Sorry for that. It should be the total sum of squares, which is 294.49. And let's work on that. 151.25 divided by that. This would give us 0.51, maybe to 2 decimal place value. Whenever we are evaluating the R squared, or the coefficient of determination class, note somewhere This is called the explanatory power of the test. The explanatory power, this is called the explanatory power of the test. It explains to us how much of the inference is by the independent variable. Explanatory power of the test. It explains to us how much of the inference are the independent variables bringing to the dependent variable, the power of the test. How the independent variables are inferencing the dependent variable. For example, having found our R squared as 0.51, remember the interpretation of the R squared is in percentage. We would say that 51% of the job satisfaction, our dependent variable Y, remember, is influenced by all these independent variables: the age, the monthly salary, the experience. All those are influencing the job satisfaction by only 51%, meaning 49% of the job satisfaction is determined by other factors which were not included in this study. I repeat, 49% of the job satisfaction must now be influenced by other factors which are not included in this study. That is how we would give the interpretation of the coefficient of determination, also called the R squared. We also call it in statistics the explanatory power of the test. Explanatory power of the test. And I've said the coefficient of determination is usually interpreted in percentages, where after you compute the value, converting it into percentage, you'll mention that that percentage is the inference we see on the dependent variable due to the independent variables. You can mention the independent variables in question, but if there are so many, you can just say the 51% of the job satisfaction is determined by the independent variables in this analysis, whereas the 49% is determined by other variables that were not included in the study. We all know the coefficient of determination, R squared, is related to what we call the product movement coefficient of determination, or rather the coefficient of correlation, sorry. We all know the coefficient of determination is related to what we call the product movement coefficient of correlation. The product movement coefficient of correlation is small r. So if we want to find what is the coefficient of the product movement coefficient of correlation, the small r, we are going to take it as the square root of the R squared. And to find that, we are going to consider the sum of squares under the regression model. We divide this one by the total sum of squares, and we find the square root of that result. The sum of squares due to the regression, we divide this one by the total sum of squares. That will give us our small r. For example, if our R squared is 0.51, the square root of that would give us 0.72. What is the comment of this? The comment of our R now would say is that there exists a strong positive relationship. This is a positive value, as you can see. There exists a strong positive relationship between the level of job satisfaction and the variables in question, whichever were given as the independent variables. But in a shorter way, once we have our coefficient of determination, the R squared, it is also possible for one to determine the product movement coefficient of correlation using the Anova table. That is the square root of the sum of squares of the regression divided by the total sum of squares, and of course you find the square root of that. So I hope that one is clear as much as the Anova table interpretation is concerned. Now, we had said earlier, the total degrees of freedom are usually given by n minus 1. The total degrees of freedom equals to n minus 1. And in our case, because we were given this is a total of 49, in other words, the regression model has the degrees of freedom. You add it to that of the residue or the error term, giving you a particular total. If you are to take that total as n minus 1, then in this case, we have our n equivalent to 50. Why am I interested on n? Let's look at the next question. Part number 3. Test the significance of each variable in explaining the level of job satisfaction among the employees. And you are told to use the significance level of 5%. Use the significance level of 5%. Before we test, we need to find out what is our the t statistical value for each of our independent variables. This is something that we did in the bivariate analysis where we had only one x, but now we have so many variables. So for each we need to do a test.